Hello, and thank you for joining me today as we begin the last little section of this unit on electrons in the periodic table. So today we're going to talk about periodic trends. So we're going to give you some terms, and we're going to look at how that changes as you go across the periodic table or up and down the periodic table. And this is why that periodic law is so important and where it comes into play and makes things so easy, and we can make sense of it all. So let's get started. So today, you will be able to, at the end of this, define atomic radius, electronegativity, and ionization energy. You will be able to compare properties of elements by understanding the trends. So if I give you two elements, you can compare which one's got a higher electronegativity, lower electronegativity, larger atomic radius, more ionization energy, so on and so forth. We're going to look at how reactivity is related to the trends on the periodic table. So how does your ionization energy and your atomic radius affect your reactivity? And we're going to look at differences in melting and boiling points of metals and nonmetals. So those four things are what we want to accomplish today. So for starters, we have atomic radius, and I didn't actually give you a definition for atomic radius. So atomic radius is the distance between two nuclei of the same atom bonded together. Same element bonded together. So it's not, I guess it's half the distance, because the radius is only half diameter to be the whole. So half the distance between two nuclei of the same element bonded together, essentially from the nucleus to the outermost electron. Nucleus to electron. Okay, that's your atomic radius. The trend for this, so as your atomic number increases, so as you go from left to right, increases in a group. So as you go from top to bottom, your atomic radius goes up. So going down a group, there are more electron energy levels surrounding the nucleus. So if we have hydrogen, hydrogen's got a single electron here. If we go to lithium, which is right below that, we have 2 electrons, then we have this outermost has 1. You'll notice this circle is smaller than this circle because my radius got bigger. So as you go down a group, there are more electron energy levels, which means it's got a bigger atomic radius. So the distance from the nucleus to the outermost electron goes up because you are adding those energy levels. As you go from left to right on the periodic table, your atomic radius actually gets smaller. So if we look at group 2, or period 2, we have lithium, we have beryllium, we have boron, we have carbon, we have nitrogen, we have oxygen, we have fluorine, and we leave off the noble gases because they do their own thing. Okay, but lithium, what's happening here is we're adding a proton to the nucleus. Ooh, sorry, yeah, 8 protons and 9 protons. So because your atomic number is going up, you're increasing the number of protons in the nucleus, which means they're going to pull stronger. You have a stronger pull from the nucleus. So if I have a nucleus pulling on this electron, now I have 2 protons versus this one that's got, let's give it 4 protons, just for the sake of fun. This 4 protons is going to hold this closer because there's more charge. So what you're doing is you're increasing what's known as the nuclear charge, or the pull from the nucleus on the electrons, which pulls it closer, decreasing the size of an atom. So as you go across, lithium is going to be a bigger element than fluorine. So your atomic radius decreases going this way. Atomic radius decreases going across. So the lower left is going to be your largest element. I believe it's francium down there is going to be your largest element. So lower left is larger, is how you can remember atomic radius. So here is showing you different atomic radii. And so this is looking at Your lithium is here, your fluorine is here. Notice fluorine gets smaller. As I go down, each of these are bigger, but going across this way, they get smaller. So in general, as I go down, my atomic radius goes up. As I go from right to left, my atomic radius goes up. So my trend is this kind of direction. Atomic radius increases going that way. Electronegativity. This is the second term you're going to use, second trend we need to be familiar with. So your electronegativity is your attraction of an atom to pull electrons from other atoms. The big key here is from other atoms. So in a chemical bond, this is how much it wants to pull electrons from other atoms. Your trend on this, as you go from left to right, electronegativity, I'm going to call it En, goes up. As you go from bottom to top, En goes up. So this is the opposite trend of atomic radius. Atomic radius increase going from right to left and going from top to bottom. Electronegativity increases going from bottom to top and left to right. So this is, again, opposite for atomic radii. That's electronegativity. One that's very close to that is ionization energy. This is the energy required to remove an electron from an atom. So if you have a high electronegativity, it means you want to pull electrons from other atoms. You want to take this electron and pull it over to here. If you want to steal from other atoms, there's a very good chance that your electrons are held very tightly and are difficult to pull. So ionization energy is the energy required to remove one of your electrons. If you have a high attraction, every element has a high attraction for its own electrons, but some have a little bit less than others. And so the closer the electrons are to the nucleus, the greater the pull, the harder they are to pull apart. So closer electrons to the nucleus, higher ionization energy. Closer to nucleus. That means that your elements in period 2 are going to have a higher ionization energy than your elements in period 7 because they're in the second level versus the 7th level. They're closer. And so that's all this is saying is the greater attraction, the more tightly it's held, the more energy needed to remove them. Your trend increases from left to right, just like electronegativity, increases from bottom to top. So your trend is going to go this way for increasing ionization energy, from bottom left to top right. So it's the opposite for atomic radii. It's the exact same as electronegativity. Here's a look at your trends. I would encourage you to draw these on your periodic table. Off to the side, I would draw ionization energy increases going this way. Electronegativity increases going this way. I would do the same. I don't care if you put it on the side here or the side over here. I would draw them. I would draw those three. Your electron affinity and electronegativity are very close to the same thing. So I don't deal with electron affinity. I just call it electronegativity. But those three, electronegativity, ionization energy, and atomic radius, you need to be familiar with as far as trends go, because we're going to use this. A couple things to finish up. We're going to talk melting and boiling points. So we're talking about metals. So metals within a group, as you go down the family, so as you go from top to bottom, your melting and boiling points increase. Or they tend to decrease. I apologize, I wrote the wrong thing. Your melting points and boiling points decrease as you go down a group. For nonmetals, as you go down a column, your melting point and boiling point go up. They require more energy to melt and boil as you go farther down the list, whereas metals, the melting and boiling points decrease. So that's the difference between metals and nonmetals in terms of melting and boiling points. If we're talking densities, densities tend to increase as the atomic number increases. So as you go from left to right, density goes up. As you go from top to bottom, your density goes up. So density almost goes this way. As your atomic number increases, your density goes up in general. There's a couple exceptions to that, but in general, that's how your density works. If we look at elements and try to figure out, if we look at ions, so ions are atoms with a charge. If we're talking metallic ions, remember metals form cations, meaning they lose one or more electrons. When they do that, or I guess in order to do that, you have to pull that electron away. And so your metals that are farther down a group, so as you go lithium, sodium, potassium, and then I believe it's rubidium after that. As you do that, you're going down, you're increasing the distance from the nucleus. So as you get farther out, it's easier to lose that electron. You need less energy, so it's easier to remove electrons from these bottom substances. And when those metal atoms lose electrons, they become positive, and your ion, a positive ion, is smaller than the atom it came from. So a sodium atom, a neutral sodium atom is here. When it loses that electron, it loses that outer energy level, which means that it's going to shrink because that energy level, that whole energy level is gone. So we lost all of this because that one electron was taken. Ooh, that was really bad. Because that one electron was taken away. We lost this entire energy level. And so our atom is going to shrink. So if metal atoms shrink, that means that non-metal atoms are going to gain that electron. And because they gain it, your negative ions are going to be larger than the atoms from which they form. So non-metal ions, negative ions, and ions are going to be larger than their neutral atom. Metal cations are going to be smaller than their neutral atoms that they form from. And all this has to deal with reactivity. So the goal of an atom is to have 8 valence electrons, or to have 0, which eliminates your outer shell. And this makes them like the noble gases. They are stable. So atoms want to become stable just like the noble gases are. So metals will lose their valence electrons and become cations. When they do this, they become a smaller ion, but the farther down you go on the table, the larger the radius of a metal, the more loosely the valence electrons are held, the easier they are to pull, which means that your most reactive metals are going to be on the bottom left side of the periodic table, which is going to be francium and cesium are going to be your 2 most reactive metals because they have the fewest valence electrons and they're farthest from the nucleus. The inverse is true for your nonmetals. Because nonmetals want to gain electrons, it's easiest to gain when they are close to the nucleus. So they're looking to complete their outer shell, whether that's gaining 1, 2, or 3 electrons, and that will give them the electron configuration of a noble gas, which is what everything wants. So the smaller your radius, the more readily your nonmetal will accept electrons. So our most reactive nonmetal is going to be fluorine. So your most reactive nonmetals are in the upper right. So fluorine and chlorine are extremely reactive, along with oxygen. Whereas francium, cesium, you can throw strontium in with that as far as reactive metals, down in that lower left-hand corner. All right, here are some questions for you to think over, think through, and answer. So 1, why does the atomic radius increase as you go down a family on the periodic table? So what is happening to the atom that makes the atomic radius go up? 2, what happens to the ionization energy of elements as you move from left to right across the table? And then be able to explain why. Why does electronegativity increase as you go up the periodic table? So as I go from bottom to top, why does my electronegativity go up? And what is electronegativity along with that? And then how do the melting and boiling points of metals and nonmetals change within a group? So look through those, be sure you're able to provide an answer for those. And I look forward to working with you through the rest of this unit and then getting into more units later on. But thank you very much for your time and attention, and enjoy the rest of your day.